Sir, can you please again explain the explicit and implicit part?
Yeah, so is it okay now? Hello? The wind sound?
Yes,
Yes,
sir.
sir.
Yes, sir.
Will it
Now
is
okay.
come?
साउंड थोड़ा बढ़ा लीजिए.
Yes.
Is it okay? Hello?
Okay,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Yes, sir. Sound okay, sir.
Okay. Well, so there is a minor correction in the definition of degree. Okay, the definition of degree is inspired by the degree of a polynomial, and which is essentially in this particular course is of finite degree. Okay, so that is the first point I wanted to correct. So therefore, so some of the examples yesterday we discussed will have some change. Yeah, so like
Sir, can you
dy,
repeat the what?
yeah, so the definition of degree is inspired by the degree of a polynomial. Okay, so a0 x to the power n, see, just a minute, a0 x to the power n if fx is a polynomial function of the form plus a1 x to the power n minus 1 plus dots up to a n minus 1 x plus n. If a0 not equal to 0, then what is the degree of fx? That is n. Deg of f is equal to n. So this is how degree of a polynomial is defined, and it is finite. It is finite. N is finite. Now, for example, if fx is equal to say x square minus 2x plus 1, although it can be written as x minus 1 whole square, but degree of f, sorry,
Is 2.
degree of f is equal to 2. Okay, and except rationalization of the powers of the derivatives, no other operation is allowed in the process. Okay, like inverse and other operations are not cos hyperbolic inverse, sine hyperbolic inverse, those operations are not allowed. Only if there is some power like m by n, okay, so m by n, then you are allowed to rationalize it. That is the operation is allowed to define the degree. So therefore, yesterday we took one example of this form, probably 2x dy dx plus x squared is equal to something, say x square plus y square, something like that. And we considered, we basically simplified it to this x square plus y square, and eventually we wrote dy dx plus x is equal to plus minus root over x square plus y square. So this type of operation is not allowed. Okay, so you see there are two different roots. So therefore, already we have the equation in the polynomial form. Polynomial in derivatives. That is very important. Polynomial in derivatives. Okay, we have to only focus on the derivative terms. Already we have the polynomial in derivative. Therefore, degree of this differential equation will be equal to 2. And order is 1, first order derivative. And some of the examples we considered, like d2y dx2 is equal to say cos dy dx and some other functions, say 2. Then this is here degree is not defined because of the involvement of this cos function. It is not a directly a polynomial function. Okay, order is 2, but degree is not degree is not defined in this case. And similarly, if we take tan dy dx is equal to say x square plus y square, inverse operation is not allowed. And if we write it as fxy is equal to tan dy dx minus x square minus y square, so therefore it is not a polynomial function, it is rather a involves a tan function of the derivative, so degree is not defined. Okay, so this is how we will find degree. So for example, cos dx is equal to say x plus y. So in this case also either we can expand, but will not do that. We will directly compare this equation with some polynomial. If it is not a polynomial function, it involves cos, sine, tan, exponential, log, etc. We'll say that degree is not defined. That's it.
Sir,
Value is oscillating,
sir,
therefore it is
degree
appealing.
fine, sir. Sir, cos divided by dx is equal to x plus y, na, sir. Degree defined 1, sir. Order 1, degree 1, sir.
No, degree will not, so it is not a polynomial function, cos function of the derivative, you see. If
No,
we
sir,
write,
in this case defined, sir.
So, but we can transfer it to other side.
no, that translation is not allowed equally. While defining the
Inverse
degree,
is not
only
allowed now.
transformation is not allowed. Only thing is that we can do, for example, we took one differential equation of the form 1 plus say dy dx whole to the power 3 by 2, something like that, or 5 by 2, I don't remember. So in that case, we can rationalize the power. So that operation only allowed. Then directly we have to compare it with the polynomial, with a polynomial, keeping in mind that polynomial in the derivatives. Okay, other terms we will ignore. So
Expression become
cos x equals to d square y upon dx square. In that case, we will be having infinite polynomial, but under the cos term there will be no differential part like dy by dx or d square by dx square. So we will get undefined degree or some definite degree.
no, please repeat. I could not follow you.
excuse me,
Sir,
sir, can you
we
please
have like cos x
Cos x.
equals to d square up y upon dx square and some plus thing. So in that case, so like x or y some. So in this case, the it will be definite or indefinite.
Order equal to 2.
Order
That is
2,
quite
degree
clear.
1.
Degree 1.
Degree 1.
Because it is, we while comparing this with a polynomial, so we will just consider the derivative terms minus cos x.
Sir, in
equal
this
to
case,
this.
sir, 1 plus x
Right.
equal to ln dy by dx. Then
1 plus x
equal to ln dy by dx. Then
ln dy dx. This is
That-
also not defined.
Sir, but we
But
can
we
transfer
studied this
it
is
to e
defined,
की
sir.
power 1 plus x.
So that operation is not allowed.
Why,
Oh,
sir?
but
Sir, allow, sir.
teachers told
Linear
us.
रहेगा ना, sir. उसमें allow रहेगा, sir.
What?
Sir, we have studied that it should be
Yes,
allowed.
sir, it is allowed.
Yes,
sir.
allow,
We
degree 1,
study
sir.
like that.
No. So if you take
Last case, sir. Post.
dy dx, you want to write like this.
Sir, we can define a function if we can.
So if I expand it, it will be possible.
No, expansion will give you infinite series. So we'll rule
Yes,
out.
sir.
We have already ruled out the infinite series, infinite polynomial. Okay.
Sir, what about the order?
Sir, in the previous slide,
Order is 1 only.
previous slide,
Manipulating it or differentiating it, we will get different.
Yes.
sir, in this previous slide, yesterday our question is there is no plus 2, then what will be the answer, sir? Like d square y by dx square minus
Okay,
cos
let
of dy dx is equal to 0.
d square y by dx square.
dx square minus cos dy by dx is equal to 0. This is the one question, and another question is d square y by dx square whole square.
Degree not defined, order 2.
Degree.
Sir, here the thing is d square y by dx square whole square.
D square
d square y by dx square whole square minus cos dy by dx is equal to 0.
dy by, this is also degree not defined.
Sir, no, sir. It is so, sir. Whatever may be the site or Wikipedia we search, it is showing that degree is 2. That's why I confused.
Not
No,
defined.
no, no.
is the-
Yeah, you have cost function, so we don't have polynomial function. Okay. Okay, it depends actually.
Sir,
So,
but cos d by
but
dx equals
standard
plus
books,
y degree defined, sir.
see in the standard books, this is here degree is not defined, but later you will see that main point is that whether we can solve the differential equation, that is the main point of concern. Degree you can define. So here I will define degree the way I have said, that only rationalization of the powers is allowed, other operations will not allowed, and then it will be fixed. Actually, there will be no ambiguity in the definition.
Sir,
Yes.
cos d by dx equals plus y degree defined, sir. 1.
Which one?
Cos d by dx is equal to x plus y.
Cos dy by dx
is equal to x plus y.
No.
Yes,
Here
sir. Degree 1,
you
sir.
have to.
Sir, we can write it as dy by dx equal to cos inverse of x plus
So
y.
that I am not
Sir,
allowing. Actually,
linear, sir, linear defined.
in my definition, I am not allowing. Okay.
Here case it is defined.
If you can.
Sir, we might study wrong thing also.
We will do transformation, then x plus y should be from only the 0
I will
to pi.
just write the function.
That will be restriction of over the domain.
Cos dy by dx minus x minus y, and it is not a polynomial of dy dx, a derivative. So therefore degree is not defined according to the definition I am using here. And solution of a differential equation mostly will not depend on this type of different kinds of definitions of degree. Okay, so in my definition, let me be very clear that except rationalization of the powers, I will not allow any other operation to convert the equation. Okay, and then I will write the equation in terms of a function where if it is a polynomial of different powers of the derivatives, I will take the highest power of the highest order derivative. That is my degree. Okay.
Sir, what yesterday we have question like dy plus upon dx plus xy whole square equals to log x whole square. Then in case
just a minute, dy dx
plus yx whole square.
yx whole square.
Sir,
or, no, the thing you
whole
want.
Square on,
Achha, just
whole
a minute.
Whole bracket.
This
equals to log x whole square.
log x whole square. Okay,
so in this case, yesterday we wrote degree 1.
Rationalization of power is allowed, so that's why it is 1.
Yes, so rationally, so minimization of, but in this case also there are two possibilities, na? Plus minus log x.
Yes.
So degree you cannot reduce. Dy dx you will get dy dx whole square plus 2xy dy dx plus x square y square minus log x whole square. And if you just take the square root, you will get plus minus. So two factors will be there. So your fxy, you have to take both the factors. I gave you the example of a polynomial that it can be like 1 minus x square, yet its degree is 2. Okay, so in that sense, if you compare this with the polynomial, degree will be equal to 2. Degree of the differential equation is equal to 2. Okay, but this is not very important. The degree the way I am defining now, it is uniquely fixed, uniquely determined. And now I will discuss different kinds of differential equations and how to solve those things. So the methods.
Sir, can you please again explain the explicit and implicit solution once?
Yeah, that I can do. Sure.
Sir, you have said that the polynomial equation on the dy dx.
Yes, dy dx is derivatives actually. It may be higher order derivatives. Not only dy dx, it can be d2y dx2, d3y dx3. So we have to consider different powers of the derivatives, and they cannot appear as the fractional power. If they appear in fractional power, if it is possible to make it integral power, then we can define actually.
Sir, if inverse function is directly given in the question, then degree is defined or not?
Degree is defined. Directly given, degree is defined then.
Sir, like dy by dx is equal
to cos inverse x or plus y, something like that, then degree is
defined or
defined.
not?
Degree is defined in that case. Well, so explicit solution means this is the general form of the differential equation. This is the general form of the differential equation we will consider in the discussion. It may involve x, y, independent variable and derivatives of different orders. And depending on the highest order derivative, order of the differential equation will be defined. Now, explicit solution. Explicit solution means it is basically a function of x. F, we call it f, small f, and it must be defined in a real interval. Okay, it must be defined in a real interval. And moreover, when we substitute f in place of y, when we substitute f in place of y, it should satisfy the differential equation. Okay, it should satisfy the differential equation. That means you see we have just replaced y by f, which is a function of x defined in a real interval. Okay, and once it is substituted in place of y, the relation is satisfied. Okay, that means f of x, fy, f dash x, fx, f dash x, so on f n x, that is equal to 0 for all x belongs to I, where the function I is defined, a function f is defined. Explicit solution, is it clear?
Sir, can you take an example? I did
Yes,
not
sir.
get it.
Yeah, I gave one example. You see here, explicit solution. Fx is equal to 4 sin x minus 3 cos x. It is defined in the entire real line. And it will satisfy this differential equation. That means if you substitute fx in place of y, left hand side will be equal to right hand side. So therefore it is an explicit solution of this differential equation. Okay.
Yes, sir.
And
Okay,
implicit
Explain the sir, please explain the definition by this example.
Yeah, so you see here, just a minute. Here fx is equal to 4 sin x minus 3 cos x. Okay, and fx is defined for all x belongs to R. Your interval is now the entire real line. Okay. Now, if you put f, that means d2f dx2 plus f. So in place of y, we are putting f. Then what we will get, d2x square 4 sin x minus 3 cos x plus 4 sin x minus 3 cos x. You calculate it,
Minus
you will
4
get
sin
it.
x plus 3 cos x plus 4 sin minus 3 cos x is equal to 0, sir. It's getting
Equal to 0. So that means the function is satisfying the differential equation.
Yes, sir.
Okay, therefore this is an and moreover f is expressed as a function exclusively as a function of x only, and it is defined in a real interval. Okay, so therefore it is an explicit solution. And for implicit solution, we'll get a relation between x and y. Okay, which will satisfy the differential equation first of all, and then moreover, what we can do from this implicit relation, we can extract a valid explicit solution. From this implicit solution, we can extract a valid explicit solution. For example, in this case, x square plus y square minus 25 equal to 0 is an implicit solution of the differential equation y dy dx plus x is equal to 0. So how we can check this? First of all, you start with this implicit relation x square plus y square minus 25 equal to 0. You will get, if you differentiate, you will get 2x plus 2y dy dx equal to 0. That means, which means x plus y dy dx equal to 0. That means this implicit relation is satisfying the differential equation. And moreover, what we can do from this relation, given relation, we can So this is the given relation which is satisfying the differential equation, and we can define two functions of x given by 25 minus x square plus minus. Both of these functions will satisfy the differential equation, and these functions are defined within the closed interval I minus 5 to 5. That means from the implicit relation we should be able to extract at least one explicit solution. In this case we are able to extract two explicit solutions. Okay, y is equal to root over 25 minus x square, and another one is y
X
is
square
equal to
minus 25.
x square minus 25. No, minus root over 25 minus x square.
Yes, sir. Minus root.
No,
Yeah.
so it is correct.
Yeah. So then both of these functions will satisfy the differential equation, and they are defined in a valid real interval minus 5 to 5. And beyond this interval, it is not defined. That is not required in the definition. So therefore, x square plus y square minus 25 is equal to 0. It is an implicit solution. And apart from that, in most of the cases, in many cases, not most of the cases, there will be some function like x square plus y square plus 25 equal to 0. In this case, it will satisfy the differential equation, but you cannot extract some valid explicit solution from this relation. It is merely satisfying the differential equation, but we cannot find or cannot define an explicit solution from this relation. Therefore, it is a formal solution of the differential equation, but not an implicit solution. Okay, because if you write this, say minus x square minus 25 root over, it is not a real number. Okay, we are dealing with real functions and real differential equations. So therefore, we cannot extract an explicit solution from this. And it is a formal solution because it is satisfying the differential equation, but it is not an implicit solution. Okay. But most of the cases, while solving problems, we will not focus on this part. We will just be busy to find the implicit relation which will satisfy the differential equation. Rather, we are trying to find the formal solutions. Okay, but if you really want to get a valid solution, we should have an explicit solution from the, we should be able to extract some valid explicit solution from the derived formal solution. Well, so this part we have already done. Yeah, this is the important theorem. So by now we have understood that many physical as well as engineering problems or man-made problems mathematically modeled using differential equations. Some of the examples I have mentioned already. Now, next we understood that once we have the differential equation together with some additional conditions, we are interested to find the solution of it. Okay, and we will try to find the solution of the differential equation or the problem involving the differential equation. But before that, it would be nice if theoretically we can assure that solution at all exists. Otherwise, it may happen that after working for years to find a solution of a complicated differential equation, we might land up to the conclusion that there does not exist any solution of the differential equation. So that is not good. So therefore, it will be nice if there exists some theorems called existence theorem, and along with that we can talk about the uniqueness of the solution. Then it will be very nice theoretical support to solve a particular problem involving differential equation. One such very simple existence and uniqueness theorem is called Picard's theorem. So what is the statement of it? It is very simple. We are dealing with first order ordinary differential equation, first order and first degree. dy dx is equal to fxy. This is the differential equation. And then we also know that this fxy is continuous in a domain D. Okay. The domain of definition is a portion of the two-dimensional plane in this case, because we have two variables x and y, portion of the two-dimensional plane. And within that portion, f is continuous as well as del f del y. Partial derivative of this function with respect to y is also continuous in that domain. And you take a point x0, y0 from that domain D. Suppose this is the domain of definition of the function, is a portion of the plane, and within that plane, within that portion, you have a point x0, y0. Okay. Then, if this function f as well as del f del y both are continuous in this domain D, then it is assured that there exists a unique solution. Strong statement, you see. Unique solution phi of the differential equation 2 defined in some interval. This phi is defined in some interval given by x minus x0 less than equal to h. H may be very small, but still it exists. And we satisfy the condition phi x0 is equal to y0. Okay, so this is called Picard's theorem. What are the requirements? The right hand side function in the right hand side should be continuous in the domain of definition, and as well as the derivative of it with respect to y, the dependent variable y, should also be continuous within the domain D. Then existence of a unique solution passing through the point x0, y0 is guaranteed, and that unique solution phi will be defined in a valid real interval around the point x0. So this is the conclusion of the theorem. So we don't have proof of this theorem.
Here.
Yes. Please repeat.
Sir, what is phi here? Phi.
Phi is the solution. Existence of a solution of this differential equation is guaranteed. It is an explicit solution. Okay. Existence of an explicit solution of this differential equation is guaranteed, which will pass through the point x0, y0. That means it will satisfy this condition. Okay. So requirement is very simple. Function f and del f del y, they both of them should be continuous in the in that domain. Then existence of a unique solution passing through the point x0, y0 is guaranteed. And this phi, the existence of the unique solution phi, so this phi will be defined in an interval, real interval around x0, given by x minus x0 less than is equal to h. Okay.
So can you show it with an example if possible?
Yes, examples I have. Yeah. Immediately it will follow with examples. Okay, you consider the first example, dy ds is equal to x square plus y square.
So can you go to the previous page, sir?
Yeah.
Thank you, sir.
Yeah, so you consider the first example. What is your fxy? In case of first example, x square plus y square. It is a polynomial in x and y. Polynomial functions we already know, no need to check anything. It is sufficiently smooth. That means not only these functions are continuous, but also derivatives of all orders of a polynomial function will exist and continuous. So that is known, and you can use this. And formally proving the continuity is not very easy in many cases. Okay, in this case it is not difficult, but in many cases it is not easy to define or to check the continuity of the of a particular function. Okay, you know the definition probably, how to find or how to check the continuity of a function of two variables. Okay, a function is called continuous at a point what? AB if fxy minus fab for a given epsilon is less than epsilon whenever xy belongs to some appropriate neighborhood of AB. Okay, delta neighborhood basically, delta neighborhood of AB. So this is how continuity is defined, and from the definition itself you can easily appreciate that not always, if the function is complicated, not always it is easy to check the continuity of a particular function analytically, but numerically one can always check. How one can check numerically the continuity of a particular function? It is not
the first order derivative. The first order derivative will be either positive or either negative.
No, that is probably you are mixing with maxima minima thing. Faster.
Sir, you are saying about the sufficient condition.
Taking some values of x and y.
Yeah, so numerically we can take a grid. For example, we are interested in a finite portion of the plane, and we can take a very fine grid of that portion, and at each grid points we can calculate the value of the function, and at the discontinuity point, from our experience, okay, of solving different problems with the functions of single variable at the discontinuity points, so what basically happens? Either we would observe a very sharp jump in the values, or the divergence of the function at that point. Okay, and if we approach towards the point from one side, we will get one value, and if we approach from the to the point from the other side, we will get different value. That means there is some jump in the values. Okay, in the near the point of our concern. Okay, so therefore numerically, if we find the values of this function in a grid, for example, if we want to check the continuity of this function in a particular region, say this is your x equal to 0, x equal to 1, and y equal to 0, y equal to 1 unit square. Then what we can do numerically, we can just generate the grids like this. So many grids you can generate using computer, and at these grid points you just calculate the values. If at some point it is not able, you are not able to calculate, there is some point where it is undefined, then you can immediately conclude that there is a discontinuity. And moreover, you can look at the values, you can look at the surface generated. So what you can do at these points, you will get some values, and you plot all the values. If there is discontinuity, there will be some jump, abrupt behavior near that fixed point. From the surface you will see. So therefore, numerically you can check it using computer, and using MATLAB or Python, some other user-friendly languages, you can immediately draw the graph or surface. Okay, if you look at the surface, you can immediately understand whether this function is continuous or not. But analytically determining often might be very difficult. Okay, even for textbook problems, we have to use different techniques. Anyway, so that is not important. For polynomial functions, they are sufficiently smooth. We already know. Not only they are continuous, but derivatives of all orders of that polynomial function will exist, and they will be continuous. Okay, so therefore fxy is continuous, and del f del y, what is that? This is equal to 2y. It is also a polynomial in y. It is also continuous. So therefore, a continuous everywhere actually, in the entire two-dimensional plane. So therefore, in particular, if we consider the point 1, 3, so here you see x1, y1 is equal to 3. That condition is given.
Statement is that del f del x. No, in statement it is written.
No, it is del f del y. This is del f del y. Yeah. With respect to the dependent variable.
Okay, sir.
Okay. So these two are continuous in the entire two-dimensional plane, and 1, 3 is a point in that plane. Therefore, through 1, 3, a unique solution of this differential equation will pass. Okay, a unique solution of this differential equation will pass from the bigger.
How did you get the point 1, 3, sir? Can you explain?
Yeah, so y is defined. So x0 is x0 equal to y0. So this is the condition. No? So at y at x is equal to 1 is equal to 3. So this is the value of y actually of the function at x equal to 1.
So it will be given in question.
Yeah, it will be given. Now you look at the second problem. Second problem. So what is your fxy y by root x? In the second problem, our fxy is equal to y by root x, and del f del y is equal to 1 by root x.
1 by root x.
1 by root x. And this function is continuous everywhere except at x equal to 0 from the rational nature of this function. So you have one function in the numerator, another function in the denominator. This type of functions are called rational functions. Okay, so at x is equal to 0, it is discontinuous because it will diverge to infinity. And here also x is equal to 0, it is discontinuous. Okay, and in other except that point, in other places it is continuous. Both the functions are continuous. Now you look at the second problem. So what is the point of concern here? 1, 2. It is the point 1, 2. So because y at 1, that is at x equal to 1 is equal to 2. So we have to focus on the point 1, 2. So this is my two-dimensional plane. And here is the point x is equal to 0. X is equal to 0 means on the y-axis there is problematic. And point of concern is 1, 2. This is your x-axis, y-axis. This is the 1, 2. So therefore, if you take your domain, excluding this region, excluding this y-axis, suppose you take a domain, something like this. In this domain, there is absolutely no problem. Okay, so the f as well as f, del f, del y, both are continuous. So therefore, in this domain, if you consider the domain excluding the problematic points, then in that domain there is no problem. Unique solution will exist and that will pass through that point. That means which will satisfy a unique solution y is equal to phi x will exist, which will satisfy phi of 1 is equal to 2. Okay, so which is equal to y. Okay.
How you get phi is equal to 1 is equal to 2?
It is guaranteed by the Picard's theorem that there exists a unique solution phi, which will satisfy the condition phi x0 equal to y0. x0 is equal to 1. So you look at the condition x0 is equal to 1, which is written within y1 is the condition, and its value is equal to 2. That means that is your y0. x0 is 1 and y0 is equal to 2 for this particular problem. So therefore, there exists a unique solution phi. It is guaranteed. Now, don't think that we have found the solution, but it is guaranteed that there exists a solution phi which will satisfy this. And we have not found phi for this particular problem.
Sir, for such questions, sir wants to show the problems.
Yes.
The theorem.
Yes.
Sir, in the question itself, that y of 1 is equal to 2 and y of 0 is equal to 2, itself it is given or we have to find it?
It will be given. No, it will be given. It will be given.
Sir, if not, then what is the good approach? Like, how can we discuss the graph? How can we come to conclude that 1, 2 there is a discontinuity? There should be some problematic like that. Some conclusion parts.
The problem information will be given so that you can conclude something based on the Picard's theorem. So that information, sufficient information, will be given in the problem. And most of the problems will look like this. And PPG will discuss some more problems on this topic. Okay. So for the next problem, yeah, this is more interesting. Yes.
So how will we solve the first differential equation? Like 2 and 3 is very easy, but first how to solve?
X is r cos theta and y is r sin theta, and
Depending on that, we can do it, I guess.
So in this case, if you cannot solve it analytically, don't be upset because numerical techniques are already there. So do you know RK4 method or Euler's method?
Sir, like, but instead of this,
No,
what
sir.
student told us, sir, r cos theta, then we can bring only in the terms of r, right?
That is del m by del y minus del n by del.
Yes, sir.
No, r theta, if it is separable and it can be brought in the solvable for, yeah, then you can do it. But if a particular equation is not solvable analytically, then
which is not
numerically we can solve it. Okay, and most of the cases,
Sir, is it
differential equations
necessary?
are analytical solution for the differential equations are not available. Okay, so that is the thing. Yeah, so
Sir, is
someone,
it necessary to find out means we are able to find out the solution of every differential equation?
no, not necessary. And in fact, most of the cases, analytical solutions are impossible. Only what we can do, even for complicated differential equations, numerical techniques are there. That is why numerical analysis is so important. Okay, we can find numerical solutions. If analytical solutions are available only for very few differential equations. Okay, and most of the differential equations which will appear in case of real problems are not analytically solvable. Most of the problems. Okay, if you twist the function a little bit, even if let us suppose this is solvable, you just change the power of y little bit, it will not be solvable. Say you make it 2 by 3 y to the power 2 by 3, then it might not be so solvable. Okay.
Yes, sir. Even if we take r cos theta and r sin theta, then also we don't know for which how will we differentiate it with respect to r or with respect to theta, because in both cases another solutions will come.
Yeah, it might not be easy.
Yes, sir.
Okay, we are not so for this particular problem we are not interested to find the solution, but just we want to say that even if you want to use your numerical technique, existence is guaranteed. You can go ahead. Otherwise, if there does not exist any solution, then after lots of work you may find that there is no solution. So to prevent that thing, actually, that wastage of time. Okay, and in the third problem, same differential equation, but initial condition has been changed. The point has been changed. 0, 2. That is the point now. X0 is 0 and Y0 is equal to 2. We go to the, let us look at the region.
Discontinuous.
Yeah, so whatever region, whatever domain, so 0, 2. So this is the point. And here, function as well as its derivative are discontinuous. Infinite discontinuity is there at that point. Now, whatever domain you consider, including this point, in that region, it is undefined. It is discontinuous, f and del f del y. Whatever domain you consider, including this point. So therefore, Picard's theorem cannot be applied. Okay. Picard's theorem you cannot apply over here. And whenever we cannot apply Picard's theorem, then uniqueness, forget about uniqueness, then solution may exist, may not exist, so we cannot comment. Okay. And if solution exists, infinitely many solutions also may exist, so you cannot comment on the existence of the solution and number of solutions. Okay, so if Picard's theorem, conditions of the Picard's theorem are valid, are satisfied by the differential equation, then in that domain, existence of unique solution passing through a given point is guaranteed. And if Picard's theorem is not satisfied, conditions of the Picard's theorem are not satisfied, then what will happen? We cannot comment on that. Solutions may exist, may not exist, and more than one solutions also may exist. Okay, so anything can happen. So we are not focusing on those complicated aspects of the problem. So this is what we wanted to discuss about Picard's theorem. So there exist some theorems which can guarantee the existence of the solutions. Okay, existence and uniqueness of the solutions. Okay.
Sir,
Yes.
so for questions like number 2, there
Yes.
may be a lot. There may be a lot of number of domains D that we can define.
Yeah.
So is the phi unique for each of the domains?
Yeah. Yeah.
Okay, sir. Like there for every D we can define separate phis.
For every domain. What is your question? For every domain? So
for
we can
every
have infinite. So you are correct that we can have more than one or infinitely many domains surrounding that point. Okay.
Yes, sir. So then for that infinitely many phi we will get.
Yeah. So in each case, whether this phi will.
Then how phi is unique?
The phi.
Points.
So phi will be. Acha, so it is a very.
Sir, phi will be unique because sir, the phi is a condition on phi is that it should pass through
for
X.
every domain phi will
It's
exist.
not a condition on.
Whatever domain you consider, there will
point.
be. Yeah. So suppose you give me n number of domains where n is very large.
Yes, sir.
Okay. Now out of, so all the domains will include will include this point. All the domains should include this point because Picard's theorem says that the point should be in the in that particular domain. Okay, and in each case the function is unique, and in each case, say phi 1, phi 2, we get phi 2, phi n we are getting. They are unique, associated with say domain 1, domain 2.
But then the phi is not unique.
Let's see dn, but in each of the domains there will be infinitely many points. Okay, in that region, say you take the intersection of d1, d2, etc. dn. This is the minimal area, so it will have infinitely many points, and these phi 1 equal to phi 2. So let us suppose this is equal to d, etc. phi n for all x belongs to d. So inside that common region, the value should be equal, and outside what will happen, it may depend actually. If you one can design complicated examples, but inside the common region, function value of phi should be unique. Otherwise,
But then
one
phi
can.
1 will be equal to phi 2, and then it will not be unique.
No, so in the common region.
At a common point, sir. At a common point also.
Yeah, say for example something like that. So you have the point x0, y0 over here, and then in this region, so this is the common region. In this region, the values of different functions should be same, and outside it may be different. We are not bothered actually. Each cases are different. Here function something may be something else. Here may be something else. But in the common region, value of phi should be same.
Sir, no, sir, but
So,
sir, if this condition holds, sir, then for each and every solution, we can define different number of domains. So, sir, every differential equation will have many solutions, infinite number of solutions. Because, sir, for every differential equation, we can define different types of domain. If you take some shorter domain, I will take bigger domain. Sir, how?
No, my point is that in the smallest domain, smallest common region, the value of the all the functions should be same.
So, sir, phi is whatever may be the case. Phi is the intersection only.
No, not phi. The domain D is the intersection. Phi is a function.
No, sir, but for every D there may be different phis.
Every D there may be different phis. Picard's theorem.
Sir,
So
phi can be same also, na? Phi can be same also.
Phi can be same, but not necessarily. Picard's theorem
Yes,
cannot
sir.
guarantee.
Not
Actually.
necessarily.
But only thing is that at this point, the value of the functions should be same. All the functions.
Yes, sir. That is the confirm.
Yeah, so I think more anything else we cannot say. So within D1, x0, y0 always be a point of D1. And x0, y0 is also a point of D2. So on, x0, y0 will be a point of Dn. And in all the cases, it should satisfy phi 1 x0 should be is equal to y0. Phi 2 x0 should be is equal to y0. So on, phi n x0 is equal to y0. And whether these functions, individual functions are equal or not, that cannot be concluded, I think, from the Picker's theorem. That information is not there. So only thing is that there will be a unique function phi 1 depending on the domain which will satisfy this condition. Okay, if you change the domain and keep the same point, in that case whether you will get the same functions, I think it is not possible to conclude from the Picker's theorem. That's it.
Then how we will conclude?
Phi is the solution of the differential equation.
Please repeat.
Is phi
Then how
the
we will conclude that they will be same or different?
No, not necessarily. At least one solution is there, depending if you give me one domain and if the function f as well as del f del y are continuous in that domain, then there exists a unique function. And if you change the domain, then function may change or may remain same. Actually, function cannot remain same because in two different domains, if you change the domain of definition to functions, then functions are automatically different, even if at some points their values are same. Technically, they are different functions. Okay, if what happened? Hello. Yeah.
Phi is the solution of the differential equation, sir.
Yes. Yes.
Or if the Picker's theorem is not satisfied, then we can say that it is not having unique solution. It might be infinity or no solution.
Infinitely many solutions. Number of solutions we cannot assure actually. It may not be, there may not exist any solution, or there may exist infinitely many, more than one solutions. So it depends on the problem.
We can say for sure it does not have unique solution.
Yeah. Unique solution is not guaranteed. For sure.
Sir?
Yes.
Sir, next slide. No, sir. Where you drawn the x and y axis? No, sir. It's previous.
Yeah.
Yes, sir. Sir, here you marked that x is equal to 0. So it will be the example 3. So, sir, phi of 0 it should be equal to 2, not phi of 1.
Here.
Yes, sir. It is example 3, na?
It is example 3. And in example 1, 2 also phi of 1 is equal to 2.
Yes, sir. But in example 3, x is 0, sir. So phi of 0 should be equal to 2, not phi of 1.
Yeah, phi of 0. Here's uniqueness is not guaranteed. Actually, I did not.
For question 2 on
0.0 phi is not continuous. Del f by del
X
y
equal
is
to
not
0, x equal to 0 to the function is function as well as the derivative, y derivative is not continuous. So therefore we cannot use Picker's theorem for that problem.
Okay.
Okay. Yeah, so I think my time is over. Yeah.
So can you post today's notes and last day's notes?
Yeah, so let me do it right now. Yesterday I forgot.
Okay, sir. Thank you, sir.
Okay, thank
Sir,
you.
in which channel you will upload, sir?
In the file section, in the general channel.
Maths second, sir.
Yes, yes.
Okay.
So can we leave now?
Yeah, sure. Let
Thank
me
you.
just.
Thank you.
Yeah, so
Thank you, sir.
thank you for your interaction.